Problem 9.17. The pressure-specific volume diagram of the air standard Lenore cycle is shown below. The cycle consists of constant volume heat addition, isentropic expansion, and constant pressure compression. For the cycle, P1 is 14.7 lbf per inches squared, and T1 is 540 degrees Rankine. The mass of the air is 4.24 times 10 to the negative 3 pounds, and the maximum cycle temperature is 1600 degrees Rankine. Assume C of V is equal to 0.17 BTU per pounds degree Rankine, and determine for the cycle the net work in BTU and the thermal efficiency. Below we are given the pressure specific volume diagram. And by looking at this, we have that it is a closed system. And it states in the problem that the cycle consists of constant volume heat addition, isentropic expansion, and constant pressure compression. We are given that it's an ideal gas with the values of C of V is equal to 0.171 BTUs per pound degree Rankine, and C of P is equal to 0.24 BTUs pound degree Rankine, and the mass flow rate of air was equal to 4.24 times 10 to the negative 3 pounds. A asks us to find the net work of the cycle in BTUs, so that's what we're going to do. We have W dot is equal to what? We know that work of the cycle is equal to Q of the cycle. So what we need to find is Q from 1 to 2 and Q from 3 to 1. Q from 1 to 2 is equal to M times U2 minus U1, since there's no work from state 1 to state 2. So from there, we have Q from 1 to 2 is equal to M U2 minus U1. And in our equation sheet, there's an equation 3.38 that states that this becomes MC of V times T2 minus T1. So once we get that equation, we just plug in our values because we have the mass flow rate, we have C of V, we have T2 and T1. So this becomes Q from 1 to 2 is equal to 4.24 times 10 to the negative 3 pounds times 0.171 BTUs per pound degree Rankine multiplied by T2, which was 1600, minus 540, which was T1, and our degree Rankine cancel, our pounds cancel, and we're left with BTUs. So that is equal to 0.769 BTU. So star off Q from 1 to 2 because we're going to come back to it. So now that we have from Q from 1 to 2, we are going to start solving for Q from 3 to 1, which this one's going to be a little bit more difficult to solve for because there's work in the state from state 3 to 1. So we have the mass times U1 minus U3 plus the work from 3 to 1. So we're going to simplify the work we know that work from 3 to 1 is equal to the mass times the integral of P dV, which goes to mass times pressure times V1 minus V3. So you're going to plug that into that term. So your equation becomes Q from 3 to 1 is equal to mass times U1 minus U3 plus mass times pressure of V1 minus V3, which this could be simplified into a simpler equation, which states that mass times C of P times T1 minus T3. The only problem is that we have to find T3. So to solve for T3, we're going to use the equation T3 divided by T2 is equal to P3 divided by P2, all to the power of K minus 1 divided by K. We have every single term except for P2. So to solve for P2, we're going to have P2 is equal to T2 divided by T1 times P1, which we have every single term in that equation. So that simplifies to be 1600 divided by 540 multiplied by 14.7 lbf divided by inches squared. So P2 is equal to 43.6 lbf per inches squared. So now that we have pressure 2, we can find T3, and T3 is going to be equal to the pressure at state 3, which was 14.7, divided the pressure at state 2, which is 43.6, all to the power of K minus 1 divided by K, which simplifies to 0.286, and then you're going to multiply that times T2, which was 1600 degrees Rankine, and that comes out to be 1173 degrees Rankine. So now that we have T, we can go back to our equation right here. And plug in all of our variables. So we have Q from 3 to 1 is equal to 4.24 times 10 to the negative 3 times 0.24 times 540 degrees Rankine minus 1173 degrees Rankine, and that comes out to be 0.644, and that is a negative. So start off your Q from state 3 to state 1. So back at the top we have our equation, work of the cycle equals heat transfer of the cycle. So we solved for Q from 1 to 2 and Q from 3 to 1. So that gives us, we can solve for A, which is the work of the cycle is equal to Q from 3 to 1 plus Q from 1 to 2. So I plug in the values that I just highlighted, and you get 0.124 BTU. So now that we have the work of the cycle, part B will be easy to find. They ask us to find the thermal efficiency, which is equal to the work of the cycle over Qn, which would be equal to 0.124 BTU, which we just found, divided by Qn, which is 0.769, that is Q from 1 to 2, and that gives you your final answer of 16.2%. Done.